Hello everybody, I'm Michael DeVos, and this will be my fifth and final lab where we'll be covering the motion of Felix Baumgartner's free fall. So here's our introduction. I'll first discuss our goal and topics. So our goal here is to analyze experimental results of a free fall and compare them to a model we'll make on GlowScript. We'll be calculating drag force using the equation B times velocity squared, which is equal to the drag force, where B is a drag constant. Uh, And of course, the force of gravity in this case is going to be negative uh, mg times j hat. So then, as always, it's important to discuss Newton's first and second laws, um, especially Newton's second law, where velocity final equals velocity initial plus F net over m times t. So here's a special case with drag. The thing about drag is it's not constant. Air pressure affects the drag constant, so it's smaller when the altitude is higher and where the air is thinner. So in order to account for this case, in our model, what we did was we created a function that increased drag force in every iteration of the code, which is, as you can see, drag constant final equals the drag constant initial plus 1 over the altitude times the a times c, which is an arbitrary constant that we came up with through trial and error. Next, we have other constants. We have the mass of the object at 118 kilograms. We have the initial position. We have the final position. We have time at 256 seconds, max speed, and we have the initial acceleration, which is taken from an estimate of him pushing off. Here's our code, our initial conditions. As you can see here, we have the position in here, we have the velocity, we have its mass plugged in, and then here our drag constant in this case is shown at the bottom. Ooh, bear with me for a second, sorry. So here are our results. As you can see, the the height of Baumgartner is it's always decreasing, of course, because it's free fall. However, as he's at higher altitudes, you can see very clearly that decline is a lot steeper, and it slows down a lot once he reaches the atmosphere and reaches higher air pressures. Um, and then on the left, uh, you'll see the position versus time of our model, and as you can see, it does adjust where it gradually gets increases and then gradually decreases as he gets closer to the Earth's surface. This is an important thing to account for. We couldn't quite in our code make it so that the decline was quite as steep. And I think that the way that we calculated our constant C, uh, made it so that it was a lot more gradual of a decline uh, of a tapering off of the drag, um, as opposed to the model where it was very clear that it took a longer time and he had to get close to the ground before his uh, before the drag actually had a profound effect on his falling. Then finally, we have final questions. Does Felix Baumgartner change in temperature as he falls? Yes, he does. As he's falling, the closer he gets to their surface, the air pressure increases, which means that he's going to be in contact with more air particles, which is going to cause more friction, which is going to produce energy, which is going to make him increase in temperature. And then does he break the sound barrier? Clearly, right here, you can see that the speed of sound is graphed here, and Felix's speed is graphed as well. Clearly, while he was in his early stages of his fall, while he was still in space and not and the drag hadn't really kicked in for him, he definitely broke the sound barrier. So thank you. Yeah, hope everyone has a great day.